So now we're working with the subsets function, and the subsets function essentially takes in a list of values and an integer n and returns all subsets of the list with size n. And this is one of the best examples I could think of something that I like to call a use it or lose it kind of problem. Because in this problem, what we're trying to do is trying to find all combinations of something that we're working with that will get us to a certain solution. So that's much like count partitions or count change or other solutions where you don't exactly clearly see the solution, but you say that, oh, well, I'm sure there's some sort of combination that will get us to the right answer. In this, we're trying to see what are all the combinations that fulfill this requirement, and we return them. So looking at the doc test, we see that 3 subsets is the output of some sort of call to subsets. And the first thing I notice is that we iterate through 3 subsets, printing each element of 3 subsets, and each element happens to be a list. So what does that mean? Well, that means that subsets returns a list of lists. So that's going to be important for a bit later. Now, they provided a little bit of guidance for the base case, but once again, I'll deal with the recursive cases and then deal with the base cases at the very end. So, looking at this problem, we want to figure out what sort of combination will get us to our answer where we have a subset of this list that is exactly of size n. And one of the best ways to start looking at this is thinking about, oh, how do I frame this in this use it or lose it kind of problem? So whenever I try to tackle use it or lose it problem, I consider it like a tree, where our initial node, our root, is nothing. We don't have a solution at this moment. And we, at any point in time, we have the option to either, let me make that smaller. We have the option to either add an element or not add an element and move on to the next element, right? And so going a little bit deeper, these are just arbitrary numbers, but that's one idea, right? So in this case, our right hand side is to not do anything, to, in other words, lose it and move on to the next element, and the left hand side is to add the element or to use it. And we make that decision at every single step. Now the key thing to remember is that there are 2 branches in this tree, or in other words, at every point in time we have 2 decisions, which means we have 2 recursive calls, because normally the number of decisions you have to make at every single point in time is the number of recursive calls you have in a user or loser problem. So the question is now, what exactly do we have as our recursive calls? So let's think about the idea of lose it first. So we're going to say that, well, if we're going to consider lose it, that essentially means that we somehow need to indicate that we will not use the item that we are currently working on. Instead, we will move on to the next item and start from there. So writing the recursive call for that, where subsets takes in a list and n, we're going to say, oh, okay, we're not going to change n. We're not going to decrement n because we didn't use anything. So we still have n things to find. But instead of using our first item, we'll use our next item. So I propose that we do something like this, indicating that this means we're using the next item. Because in every frame, if we say that we used the first element, well, in the beginning, that would be index 0. But after this recursive call, in the recursive call, the first element becomes index 1. and then recursively that becomes index 2, index 3 as you go into the deeper and deeper frames. So this is the same thing as what I was saying. And so we would say that this is fulfilling our lose it goal. Now, we have to get to our use it goal. And our use it goal is a little bit more complicated because it's not just quite as straightforward as what I drew up here. This would, what I drew in this tree is not the most accurate thing. It was just more of a general explanation of use or lose it problems. But in this specific problem, rather than saying we use it and that means we apply it to like one list that we're building up, we want to say that we will apply the element that we are using to every list that comes out of the recursive call to subsets. Because we're going to say that we use that first element, but we have no idea whether we're going to use the rest of the elements. So if we just said something like, if we were to mirror lose it and we just said, oh, it's going to be something like list 0 plus subset, blah, 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 that's fine. But remember, what does subsets return? Well, it returns a list of lists. So it's not that we want to add 0 to this list of lists. We want to add index 0, the content index 0, to every single list that comes out of subsets. So this is very close, but we're slightly off. Instead, what we want to do is something like this, where we say list 0 plus x for x in subsets. I will abstract that away for now. And, oh, my bad. Actually, we would have this bracket right there. And as a result, this actually achieves our goal. So the question is, what should be inside of subsets? Well, like the lose it case, we got to consider what exactly is happening. In lose it, we said, oh, we're not going to use our values, so let's go find n more values from the rest of the list. In this case, we are using our value. So instead, we'll say, oh, well, I found one value. Go find n minus 1 more values. And then the main question is, what are we looking from? Are we looking from the entire list? Or are we in fact looking from just the rest of the list? As in list after and including index 1. So we're saying, all right, I've picked index 0. I'm including that in my list. Now use the rest of the list and find n minus 1 more values. Then that's different from lose it, which says use the rest of the list and find n values. So that's what our solution will be in this case. It'll be using what we wrote down there, which is just this. And if you're wondering why this is a double brackets right here, just try typing it into like Python interpreter or something, and you'll see that it actually does match up with everything else. Because if we're trying to append a value to a list, we can't just do a value plus a list. That's going to cause a problem. It needs to be the value inside of the list plus the other list. So you can just see that in a Python interpreter to understand why we do that. So once again, we have solved this problem of, okay, we figured out our use it and we figured out our lose it. Now the big problem with tree questions is, how do the two branches interact? Should they be multiplied together? Should they be the max of the two? What exactly is this problem asking us to do? Well, it's just asking us to compile the list of all these possibilities. So we have like a certain set of possibilities that we can get if we choose to include the first element, and we have a certain set of possibilities that we can get if we choose to exclude the first element. So as a result, the total set of possibilities is just us combining the two together or appending them. In other words, we just add the two because these are two lists. Now we have to deal with the base cases. And so once again, think about what is the most restrictive case possible. Well, they give us a hint. Let's think about n equals 0. So if they say that we somehow need to return all subsets of a list where we have 0 elements, well, that's not possible. You can't really have you can't answer this problem and find something with 0 elements and find all the combinations with 0 elements, except for when we consider just an empty list. So be careful right here. It might be very easy for you to say, oh, okay, that's our solution, let's move on. But remember, we established once again that this problem or this function returns a list of lists. So it's not going to be just the bracket, it's going to be an outer bracket with a set of inner brackets. So lastly, we have these blanks, and we need to figure out what else are we missing. Well, we thought about the case where n is equal to 0, which is like the smallest it can be. What about how large can n be? What is the limitation to n? In other words, can it be the case that we have a list that's length 3 and we are asked to find all the subsets of a list that are exactly length 10? In other words, the length of our list is bounded. And the thing to remember with this problem is that n can be many different numbers, but there's one specific number where we know an immediate answer. And that answer is when the length of the list is equal to n. Because if the length of the list is equal to n, we're saying give us a subset of a list of length 3 that is length 3. Well, there's only one subset like that. And so as a result, we would just return the list. But this, once again, just writing that is wrong because list is just a single list. But we return list of lists, so as a result, we have to put this in brackets. I understand that it's like really small details, but missing these things about just like list of lists and details like that might dock you a few points, and you want to try to get every single point possible. So with that, we solved this problem, and this is just once again a classic example of use it or lose it, where you want to figure out what is your use it case, what is your lose it case, how do they interact, and then deal with the specific details about the base cases afterwards.